Hey guys, this is second part of the solid principles. Let's see what we got for this lecture. So you remember that we said solid is the acronym of 5 design principles like this, and we already covered this one and this one. And today we're gonna talk about these two, Liskov substitution principle or LSP, interface segregation principle or ISP. As we said before, these principles are very useful for the class design or a few class design, few classes design, and with very minor changes, we can use them as a package design or layer design as well. All right. Let's start with the uh, Liskov substitution principle or LSP, which stands for this L guy. Okay, so since Liskov is a name, let's first start with this question that who is Liskov? So Liskov is actually Barbara Liskov. She is an American computer scientist and she introduced this principle in 1987. And she's a great computer scientist, as you see her achievement here. Maybe the most important one, as far as I know, is this Turing Award that she won in 2008. Uh, as you might know, that Turing Award is equivalent to Nobel Prize for other sciences. Okay, and Uncle Bob adopted his LSP principle from this lady. Okay, our next step is to see what is this LSP statement. It says that derived classes must be substitutable for their base classes. So we need to clarify what is this derived classes and the base classes. So derived classes is equivalent to subclass or children or child class, and base class is the same as superclass. Okay, in summary, what is this statement saying? Derived class is, we should replace this with the subclasses. So let's say subclasses must be substitutable for their superclasses. So it means that if we have a superclass here, and if we have a children here, let's say B, right? This statement is saying that if you expect this guy, you can substitute that parent with these children. Okay, so here is how I reword this statement. Subclasses must be substitutable for their superclasses. All right. So I think this statement is a little bit familiar. Don't you think that we have seen this statement before? Subclasses must be substitutable for their superclass. Isn't this polymorphism? Yeah, it looks like the polymorphism. It is actually, but there are some, situation that uh, can violate this statement, right? So it's not the case that we want to say that. It is not the case that always all of the subclasses can be replaced by superclasses. All right. Okay. So probably the best way to understand this is to take a violation example, because for proving that we cannot, you know, uh, take billions of examples, but if we show you a violation example, probably it would be more clear that how this principle works. Okay, so we want to consider two classes, one rectangle and one square, right? Uh, in math, probably you have heard that a square is rectangle, but with what? With restriction that the square sides are equal. But you know, from the property point of view, square has all of the properties of rectangle. So somehow it is a rectangle, but with one limitation. Sides are equal, right? So in math, definitely this is a true statement. And this relationship in math is a true statement. Square is a rectangle. But now the question raises here, is this the same in computer science? Can we use an inheritance for square and rectangle like this? Yeah, okay. So if it is true, right? If it is a true statement, and if always square and rectangle are parent and child, then I should be able to use a polymorphic a statement, and I can be we might be able to use a polymorphic syntax to represent this relationship. Okay, so polymorphism, you remember this definition, that you know that's the ability to assign or pass a child object whenever the parent object are expected, right? So in an polymorphic syntax, I should be able to assign a square to a rectangle reference. Yeah, let's see how it works in practice. So I would have a live demo, but before that, let me explain that what I'm gonna do. So this is the rectangle class. Look at this. We just have two instance fields, width and height, and for simplicity, I just mentioned the setters, both of them, because getters, doesn't have any role here. And also I added this method to calculate the area of the rectangle. All right. And for the square just extends this rectangle class, and we don't need to specify this instance field. We just use this set width and set height. But when the user calls set width, we have to set both of them at this with the same size, I mean, right? So set width will set the height and width with the same size, and set height do the same thing. In this way, we can actually simulate a a rectangle that has all sides equal. Okay, so shortly I will show you the live demo, but before that, let me explain here. So this is the UML diagram, the relationship between these two. So these are the instance fields and these three methods, and square will inherit all of this, but we had to override these two methods, set width and set height. So all of these explanations are here for your reference. You can read it later, right? So now let me bring up my Eclipse and have a live demo. To save some time, I have already created this rectangle and this square class here as I described. Okay, so now I want to test it by creating a test case. So as a reminder, we just go to here and search for JUnit. Okay, so the setting here, since we want to use the Jupyter or JUnit 5, just make sure that you click here, and the rest of this looks good to me. And also, yeah, I think we go to the finish. But since this is a new project, we need to add the JUnit 5. So we go here and we go to the libraries and we need to add library here, JUnit and JUnit 5, yeah, and finish. All right, apply. Okay, so now the JUnit 5 is active. All right, so let me create two test cases to test these two guys. I mean the square and rectangle. So to save some time, let me copy and paste from here. Okay, so the test case 0 is testing the rectangle. We instantiate a new rectangle, 2, 5, and 2, the width and height, and I added this assert to check that this, the expected value of the area will be 10, and this assert makes sure that everything goes well. All right. If you want to run one by one, just click on the name and then right click on the test case and go here. And when you see that the run as there is no test case, JUnit test case, you need to go to run configuration, and JUnit, under the JUnit you should see something, the test case name, I mean the class name, and make sure that this is test runner as a JUnit 5, not 4. All right. Okay, so we run that, and okay, so let me put it here. All right, the test case is green, so everything is fine. And for the square, just we can go ahead and run it. All right, so both test cases passed. Now let me add another test case, which is a polymorphic relationship. So I am going to copy that and paste it here, and instead of let me call it test 2, and here instead of a square I'm going to mention the rectangle, and this polymorphic, because of that inheritance, works fine here, right? And we expect that since we are here, it is calling the set width, that it will set both the width and height, right? So both of them will be 5, and the result is 25 as expected. Let me run this guy and see what would happen. Yeah, you see, again, it is fine. Okay, let's see what we got here. So we already explained this rectangle test cases and these polymorphic test cases. Now if a problem is showing up. Let's see how. So I'm going to add two different preconditions to the superclass and subclass, which is the rectangle and square. And I try to make some test cases and see the role of the preconditions when they are different for the superclass and different subclass, and let's see what would happen. But before that, let me mention two conventions that we are going to use. So if we want to add a precondition to a method, right, I have to simulate that in my test case. And for simulation, I just add a Java assertion at the beginning of the method, all right, as I will show you in the live demo. And for the post condition, we use again a Java assertion at the end of the method. I mean, right before we end the method, all right? Another convention we use is two, idioms, stronger and weaker. When we use the keyword stronger for the precondition or post condition, it means it is more restricted. What does it mean? For example, if I say at the beginning of the method height should be greater than 0, and if I say somewhere else that height should be less than 10, then since the height less than 10 is more restricted than height greater than 0, so we would say height less than 10 is a stronger preconditions with respect to this one, right? Okay, so let me show you the code here in the slide, and then I will show you on the live demo. So as you see on the set width for the rectangle class, I am going to add this assertion. From the syntax point of view, it's a little bit different than whatever we use in the test cases. So this is Java, the pure Java, but the one that we use in test case is actually from the JUnit framework. All right. So this is our precondition for set width for the rectangle, right? And of course we have the same thing here. For simplicity, I am using the same thing. And for the square class, we have this assertion, which is more restricted. So it's a W greater than 0, but here we are saying that this S is less than 10. So, bottom line is we are using a stronger precondition for the square class. All right, the subclass has a stronger precondition. And after this, I am going to create this test case for the rectangle, which should be fine because this 15 is greater than 0. So it just called the set height of the rectangle and everything is fine. But if I create this test case for the for the square, then it will fail. Why it is going to fail? Because 15 is greater than 10, and we said that the side should be less than 10, right? So in this polymorphic relationship, definitely the test case will fail. Okay, let me create a test case for here. So this test case is just testing the rectangle, and we predict that it should pass Actually, I need to add these preconditions here. So assert 15 W should be W greater than 0, and we put the same thing here for the age, and for the square the precondition will be s less than 10, and the same thing here. Okay, so the test case for the rectangle should pass. Let's test it. Yeah, as you see, this is passed. But if I use a polymorphic relationship, since it's going to call the so here we have rectangle, but here we have a square, so the square object will be the main thing. So it's going to call the set height of the square, right? And since the square uh, precondition is less than 10, but we assign 15 here, definitely this should fail. Okay, let me run it. Make sure that this is JUnit 5. And you see it failed. Okay, this is our first conclusion. Precondition of subclass should be either the same as of the superclass or weaker, because we saw that if we if we put a stronger precondition for the subclass, it will fail. So this conclusion is saying that precondition should be either the same or weaker than that. All right. We can have such experience with the post condition as well, but I'll leave it as an exercise for you guys, and make sure that you get what the conclusion would be. All right. Okay. Now let's dig a little bit deeper and see what would happen. I'm going to, you know, to add something, to add a method intentionally to, try to break this code. So I removed those preconditions and make a, clear rectangle and square class as we had before. Now I'm going to add a new method here and try to, break the code again, right? Okay, so here is the method that I'm going to add to my rectangle class. Look at this code. We call it, let's say, check shape, and I'm going to, pass a rectangle, and then just call the set height hard-coded to 10, the set width hard-coded to 5, and assert. Then I calculate the area, and it should be 50, right? If I write a test case like this, and really if I pass a rectangle, everything will be fine, because it just call this height and width, and then get area of the rectangle, and definitely it will be 50, right? It will, so definitely it will pass this test case. But how about this test case? if I use a polymorphic thing, do you think that it will pass? No, it won't pass. Uh, Even though I did a legal thing, because this method is a legal Java method and I added into the rectangle class. But this test case will fail because when we pass a square instead of the rectangle to this class, what would happen? So when it calls the set height of the square, it set both sides as 10. And when here it calls the set width of the square, it sets both sides to 5. So after this, we have 5 and 5, and the area will be 25, right? Not 50. So, so this test case failed because, in some cases, uh, we cannot add anything that we like. And since the square is inheriting all of the methods that we add in the rectangle class, so when we put a method like this, then it, you know, it ruins the polymorphic relationship between the square and rectangle. Okay, so here I explained that. And if we compare the rectangle in math versus in computer science, so even though in math, all squares are rectangle, but in computer science, they are not. Why is that? Because in computer science, we can add such methods that I just explained, but in math we cannot do that, right? And scientifically or mathematically, if we want to explain that, we would say width and height of rectangle can independently change, but this is not true for the squares, right? Okay, so here is the our second conclusion for uh, this LSP. So some inheritances do not work polymorphic relationship. So far, if we thought that if we have a polymorphic relationship or if we have an inheritance like that and we can use the child class wherever the parent class is expected, but now we prove that it is not the case. So we need to, be careful about what we are doing. Okay, so how can we fix this? Unfortunately, the LSP does not give us a practical um, solution for how to do that. So if LSP cannot do that, whose job is to do that? Yeah, that the designer job. So we should be careful about what we are inheriting, and fortunately for the precondition and postcondition, we have a strong conclusion for that, right? But for the other things, we don't have. So to satisfy the LSP principle, uh, yeah, as a designer, you need to think more and try to remove all of those problematic methods. So in this case, in our example, the problematic methods were the set width and set height from the rectangle, and we tried to fit it for the square, but it didn't work. So it doesn't work that way. So the best way would be to create an interface or an abstract class, and instead of this, we make the rectangle and the square as a sibling. All right. So Here is how we can fix that. So instead of this guy, we create here, I created an interface and I factor out the get area, but you can, put an abstract class here. It works, but for this simple example, probably the interface is the best way. So now what happened here? So these two guys now are siblings, not the, parent and child. Okay, so what would happen? So if you add any method here, this guy won't call it because the square won't call it because it's not the inheritance relationship anymore. And for the post condition and preconditions, we have a strong conclusion for that. Okay, so let's see one more time our LSP statement. Subclasses must be substitutable for their superclass. Okay, and what we learned here, now we have a really clear insight about the inheritance. We already know that inheritance, even though it's a powerful tool in object-oriented programming, but it has some problems. And we saw in this lecture some of them that it's not the case that you just inherit and everything is fine. No, we should be very careful, especially when you want to use the polymorphic relationship. So if you remember, I already said that we usually prefer the aggregation over inheritance. And today we saw one of those reasons. Now we have a clear understanding and insight about the preconditions and postconditions and their role in inheritance. And also one more time, we learn the importance about the abstractions, especially Java interfaces and Java, abstract class. Our next principle is interface segregation principle, or ISP, and this stands for this I. Let's see its statement. Make fine-grained interfaces that are client specific. So what is this fine-grained and what is this client and client specific? Let me first clarify them. Okay, so probably before that, what is the meaning of segregation here? It is splitting or separating, and we will see what does it mean. So fine grain, it means that we should make some interfaces with a small amount of methods, right? With some examples, I will clarify what does it mean. And also, who is the client here? The client is the caller or the implementer of that interface. And when we say it should be client specific, it means that we should put some methods in that interface that really that the implementer of that interface really they need those methods. Again, I will explain via an example. Okay, so Java interfaces, as we learned so far, is a very important thing, and we can say that it's a core structure. And we have seen so far many reasons that why they are so important, right? And in this principle, we want to focus on the content of the interfaces. We are concerned what content they should have. Okay, as usual, I am going to take an example to show you that if we violate this principle, what would be the consequence? So you remember about the animal voice game we took when we were talking about the polymorphism? So what was that? We had a cat and dog classes, and we had an animal interface. And now in this lecture, we have some new requirements. We want to change a little bit this stuff, and here are the requirements. So first of all, it's a mobile game right now, and so we are gonna add a button. Um, Actually, all of the buttons are soft buttons now because now we have a big display and we don't need those hard buttons that we had in the original game. So just remember that we said when we were explaining that we said imagine that we are in 1980s, right? Now we are 2020 and definitely the games are totally different, right? Okay, so instead of the hard buttons, now we have soft buttons. And of course, a big display that these buttons appears there. And also, when we push the cat button, which is a soft button, the picture of the cat will show up on the screen. And also when we push the voice button, the app plays the animals that we just picked, and its picture is on the screen, the voice will be played. And also we have the ability to set the color and the size of the animal. Okay. So the animal interface looks like this. Um, the set color, set size, and the played voice. And as usual, our cat and dog classes need to implement these methods. And for simplicity, we are not concerned how we want to implement this method because, as I said, in this principle, we are concerned about the content of the interface. So these methods are important for us, right? So we ignore how uh, they are gonna be implemented, and also we just ignore that there are some simplifications. We can factor out some of the methods into the uh, let's say an abstract class and this kind of thing. Just ignore about them and follow um, the slides. Okay, so what is the cat class look like? It looks like this. So cat, as usual, implements the animal, and we need to implement all of the methods of the animal interface. And the same we have for the dog. There is no difference here. And here is the UML class diagram, current UML class diagram. So we have three methods here, and all of these three methods needs to be implemented in the concrete classes. Okay, how about the new requirement? So the new requirement will change this configuration that we have seen so far. Let's say that in our next version, we are going to add some other stuff. For example, we are going to add a soft button called walk. So when the user or the player will push on this button, whatever we are seeing on the screen start walking, right? For example, cat start walking. We also want to add a new animal. Let's call it eagle, and also another button for flying. So if the animal can fly, then a new button will be, shown that if you push on that, the animal start flying. So based on these new requirements, we will need to add two methods, walk and fly, and let's say we need to add them into the current animal interface. Okay, so if we decide to do this, then our new interface looks like this. So these three, we already had that. Now we add two new methods, walk and fly. So what would be the consequence of this change in the animal interface? Definitely the all of the concrete classes should implement these two methods, right? So we need to open the cat, dog, and whatever we had, and implement. Otherwise the code won't be compiled. So these two methods should be implemented in the cat and dog class, and also we need to introduce a new class eagle, and obviously this eagle class, because it implements the animal interface, it should implement all of those five um, methods that we have. Let's take a look at the code and see how it looks like. So this is the cat method, implement animal. Up to this point, we already had, and we have seen that before. Now we added two new methods, right? It's a walk and fly. So walk makes sense. It's a cat, and because it's cat can walk. But for fly, it's a little bit controversial here. What should we do with this method? Maybe we should leave it blank, or we should decide about that because cat cannot fly. And how about the dog? Dog is the same as cat. But how about the eagle? The eagle class, as usual, it should implement the animal interface, and it should implement all of those five methods, right? So for the fly, it makes sense that eagle fly, but for walk, yeah, exactly like the fly for the cat, we should think about the walk for the eagle. Okay, now let's take a look at the UML class diagram. So this was the whatever we had before, right? Now, after this new requirement, the um, the UML diagram changes to this. So we added these two methods here that would be implemented here and here. And also we created a new class eagle that should implement all of these five methods. So what are our concern here is these three guys. So fly for the cat and dog doesn't make sense, and walk for the eagle doesn't make sense. But since they are implementing this interface, they have to implement it. at least they should mention that in the class, even though they might be left as the empty methods, but we should put them there. Otherwise, the code won't be compiled. Okay, so now let me ask you this question. Is this a good design? Yeah, just pause the video and try to answer this. Definitely you would say no, it is not, because we have some extra thing. Our interface is too fat. It is, polluted with some, unnecessary methods for some animals, which does not make sense. For example, fly for the cat doesn't make sense, or walk for the eagle doesn't make sense. So if if we design our code like this, then what is the consequence? Consequence is, we made the classes unnecessarily very busy. We would say it's, we increase the verbousness of the class, right? So unnecessarily busy, it means that with a better design, we can prevent, uh, this situation. So when we create when our class is too much busy, then we decrease the readability and maintainability of that class. The other issue we have is if we add a method in the interface, then we need to open all of those concrete classes and implement that method. And this is obviously a violation of the open-close principle. Just remember that in open-close principle, we said application and design should be in such a way that it should be open for extension, but it should be closed for the modification. But with this design that we have seen, when we add a new feature, we have to open that interface and put a method inside that, and consequently all of the concrete classes should be recompiled. And this is not good. This is a violation of this principle. Okay, so now we are asking this question: how can we fix this? We need, based on this principle, we need to segregate the fat interface into a smaller one. So it means that we should split that big interface into some smaller one. So, for example, this is one way that I suggest here. We split the animal interface into three smaller interfaces. One is called walkable animal, the other one is flyable animal, and the third one is a regular animal. Okay. One thing I would like to mention here, this able that we added here is a convention for naming the interfaces. You remember I said for distinguishing between the interfaces and classes, usually we add an int, for example, at the end, or even I at the beginning, or something like that to show that it is an interface. But this able that we just added here and here, flyable, yeah, that's a convenient way to um, name the interfaces. So now let's see the UML diagram. And you remember we said we were concerned about these two. Now, here is our new design. Walkable animal, it just have this walk method. Flyable animal, it has fly method, and all of those common methods goes to animal, which is set color, set size, and play voice. We didn't have any problem with this, right? And now the cat and also the dog implements these two interfaces just fit into the cat animal. No extra thing. So the cat will, implement walk from here and this tree from here. No fly is required here. And how about for the eagle? Eagle will implement this guy, right? Fly goes here and this tree goes here. So with this design, which is very compact design, we don't have that problems that we just mentioned in the previous slide. Okay, now let's take a look at the code and see how the code is changed. So animal, it just have these three methods. Walkable has just one method like this. And the cat and dog will implement these two. Look at this, implements these two interfaces. All right. So now let's take a look at the statement one more time. Now, if you read it, it makes sense, right? Because everything now it's clarified. Make fine grain interfaces, the interfaces that are fit for all of the usages, for the client specific. They should be client specific, I mean, right? Nothing extra, nothing less. And also, we learned that what's the meaning of the segregation. So what we learned here, now we have a clearer insight about what the contents of the interface. This is our new knowledge. The contents of the interface are very important. And also, with a simple example, we learn how we can segregate or split a fat interface into the smaller one. And also, we learn that how, with this principle, we can design a software that cope with the change and complexity. I'm gonna stop here, guys. See you guys in the next lecture.